Let us look at the relation of congruence in a group. So let H be a subgroup of G and A and B be in G, where the group operation is star. Now, if A is in B star H, subgroup H, then B inverse times A is in H. So here, B times H, this is a left coset. So if an element is there in a left coset, then B inverse times A is in H. So we define A is congruent to B mod H if and only if B inverse times A is in H. So here what we are saying is A is equivalent to B via group operations and inverses. The difference between A and B lies in H. When we say difference, we are talking not necessarily in terms of subtraction, but in terms of the operation of the group. So A and B lie in the same left coset, A times H equal to B times H. In case of an additive group, A plus minus B is equal to A minus B, which will also be there in H. In case of multiplicative group, B inverse times A is in H. A and B belong to the same equivalence class defined by H. This relation is an equivalence relation since it satisfies reflexivity. So A is congruent to A mod H for all A in G. That means A inverse times A is equal to E, which is in H, because H is a subgroup. Symmetry. A is congruent to B mod H if and only if B is congruent to A mod H. What does that mean? If B inverse times A is in H, then its inverse is also in H. So its inverse would be B inverse times A inverse, which is equal to A inverse times B is also in H because of the closure of the inverses. Transitivity. A is congruent to B mod H and B is congruent to C mod H implies A is congruent to C mod H. Here, B inverse times A. When we say A is congruent to B mod H, we mean B inverse times A is in H. Similarly, B is congruent to C mod H, means C inverse times B is in H. So if we have these two, it means C inverse times A is in H. Now this is pretty abstract. So let's look at an example and understand this. So we have a group of integers under addition and a subgroup is 3 times Z. Here H is a subgroup of G. So since it is under addition, we say A is congruent to B mod H if and only if A plus minus B is in H. That is, A minus B is in H, where A and B are in the same coset. So with respect to this particular example, A is congruent to B mod 3Z if and only if A minus B is divisible by 3. So here, let's figure out the cosets of 3Z in Z. So we have dot dot dots minus 6 minus 3 0 3 6 9 dot dot dot. And here, if you subtract any of these two elements, 9 minus minus 6, that is 9 plus 6, 15 is divisible by 3. So subtract any of these two, you will get a number divisible by 3. Another way of looking at it is that if we divide any of these numbers by 3, we get a remainder 0. Similarly, we have this coset dot 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 -5 -2 1 4 7 10 dot dot dot. Again, if you subtract any of these two elements, you will get a number which is divisible by 3. Or in other words, if you divide any of these numbers by 3, you will get a remainder 1. And finally, we have this. Now here, since dividing any of these by 3 gives you a remainder 0, we call it the identity coset. So these are the equivalence classes and a partition Z. Now let's look at the equivalence properties. Reflexive, for any A in Z, A minus A equal to 0 in 3Z, because 0 is in 3Z. So A is congruent to A mod 3Z. Coming to symmetricity. So symmetric, if A is congruent to B, then A minus B is in 3Z, which implies B minus A, which can be written as minus A minus B, is in 3Z. So if A minus B is in 3Z, its inverse is also in 3Z. So B is congruent to A mod 3Z. Transitivity. If A is congruent to B and B is congruent to C, what does that mean? It means A minus B is in 3Z and B minus C is in 3Z. Now let's add these two up. We get A minus B plus B minus C is equal to B cancels out. So we are left with A minus C. So that is also in 3Z. So here congruent modulo 3Z is an equivalence relation on Z, and the equivalence classes correspond to the cosets of the subgroup 3Z. In general, the equivalence classes under congruence mod H are the cosets A times H of H in G. That was one example. Now let's look at another example. Let's take this group, which is S3. Remember this, we have already seen this. This is the permutation group. Let H be generated by the permutation 1, 2. So what will it generate? It will generate E, 1, 2. So here our congruence relation will be A is congruent to B mod H if and only if B inverse times A is in H. So let's see how we can make sure that we understand what this means. The cosets of H in G are, and we have already seen this, E, permutation 1, 2, permutation 1, 3, permutation 1, 2, 3, permutation 2, 3, and permutation 1, 3, 2. So we have 3 cosets. Let's see in the first coset, what is happening? E inverse is E and 12 inverse is 12. This is just so that we can look at the next 3 steps easily. Now E inverse times E is equal to E, which is there in the subgroup H. 12 inverse times 12 is equal to E, that is in H, and 12 inverse times E is equal to 12. Now, how did we arrive at this? Because inverse of 12 is 12. So even if we multiply it with the identity, it would actually be inverse of 12, but since it is equal to 12, we write it as permutation 1, 2 being in H. Okay, now let's look at the second coset. 13 inverse is 13 and permutation 1, 2, 3 inverse is 132. So now 13 inverse times 13 is equal to E, which is in H. 13 inverse times 123 is equal to 13 inverse is 13. So 13 times 123, which is equal to 12, which is in H. Okay. Now permutation 123 inverse times 123 is equal to E, which is also in H. So we are seeing that the operation carried out between two elements of a coset based on this definition, the resulting element remains in H. Now let's look at the third coset. In the third coset, we have 23 inverse, that is 23. 132 inverse is 123. So let's take it one by one. 23 inverse times 23 is E, which is in H. 23 inverse times 132, which is 23 times 132, which is equal to 12. And 12 is in H. Inverse of 132 times 132 is equal to E, which is also in H. So take these two elements and their inverses and carry out these operations. You will notice that the results are always in the subgroup. So these are the equivalence classes and they partition G. So these three cosets are the equivalence classes and they partition G. Again, let's look at the equivalence properties. Reflexive, for any A in G, A inverse times A is equal to E, which is in H. So A is congruent to A mod H. Symmetric, if A is congruent to B, then B inverse times A is in H. So since B inverse times A is in H, its inverse B inverse times A, the whole inverse, is also in H, H being a subgroup. So we can say B is congruent to A mod H. So which means A is congruent to B mod H, then B is congruent to A mod H. Transitive, assuming A is congruent to B and B is congruent to C, then B inverse times A is in H based on our definition itself, and C inverse times B is in H, again based on the definition. So we have C inverse times B times B inverse times A is equal to C inverse times B inverse times A, which is equal to, now here B times B inverse is E. So C inverse times E times A, which is equal to C inverse times A. So we have the equivalence classes in S3 under equivalence or congruence mod H are the cosets of the subgroup H. That was relation of congruence in a group. Again, let me remind you, there is a link to a PDF book which describes all these in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now. Bye.